Hello, this is presentation number 4 on our magnetism electromagnetism unit. Today's learning targets will be you explain how the movement of electricity can cause magnetism, and you'll be able to create a solenoid. Here are where the slotted notes begin. They're going to begin at this part of electromagnetism. So first we're going to jump into electromagnetism, and it comes from the words electro and magnetism. So if you put those two words together, you see that it's electricity and magnetism. So it's the interaction between electricity and magnetism. So we're going to use electricity to create magnetism. And if you can see by this picture here, if you remember what electricity is in its basic form, it's just the flow of electrons. So as we flow the electrons through a wire, such as this, as we flow electrons through the wire, it's going to create a magnetic field around that wire. And that wire the electrons make a weak magnetic field throughout the wire. And when we couple them together and get them all together, we'll make a large magnetic field. So magnetism from electricity was discovered in 1820 by a Danish physicist named Hans Christian Ørsted. And he discovered that electricity and magnetism were related. He actually had a compass, and he placed it near a wire that was carrying electric current. And he noticed that when he did that, the compass actually changed the direction it was pointing in. And if you remember, back in a couple lessons before, we learned that the needle of a compass is a magnet, and it's also it works off the Earth's natural magnetic field. So whenever he placed the compass near a wire that had electricity going through it, he noticed that compass, rather than working off of the Earth's magnetic field, it actually worked off that wire's. And when he did that, he thought, hey, wait a minute. Compasses only work with magnetism, and that's got electricity through it. So he kind of put the two and two together to realize that the flow of electricity can cause magnetism. This is just a diagram showing you how that works. So if you have an energy source, right, and you got a conductor, and you flow the electrons through the wire, okay, you notice that as electric current flows in this direction, that the compasses move in a certain direction. And if you were to reverse the polarity, which means change it from positive negative to negative positive, change the flow of the electrons, that it makes the compasses flow or change in a clockwise formation. So if you look here at just look at this one, okay, when it flows this way, the north is pointing to the left. Now when we change polarity and the electrons are flowing this way, you see that the north is pointing to the right. So depending on which way that the electrons flow is to when how the compasses change. So moving charges, which is electrons, okay, electrons are the outside charges around the nucleus of an atom. As they flow, they produce a magnetic field around the wire. So if this is the wire here, okay, and the electron flow is coming this way, then it's flowing in a counterclockwise formation right here. If it's flowing to the right, you'll see a clockwise formation. So it all depends on which way that the current is moving as to which way the magnetic field is pulling. Now, we saw on a bar magnet, the magnetic field kind of went from north to south, and they flowed back around in a circle. Same thing in a wire. So as the wire is carrying electrons through it, the magnetic field is actually around the wire, like as you see in this picture here. So each one of these is their own magnetic field. And they'd be very weak by themselves. So if you have one by itself, or if you were to isolate this one part, it would be very, very weak compared to if you put them all together. Now, as the current increases through the wire, okay, if the current increases through a wire, then the magnetic field increases. So if we have just a small amount of current, like 3 amps running through it, then it would have a very small magnetic field. But if we were to increase that current to, let's say, 30 amps, then that would, of course, increase the magnetic field. So they're related. So the current of the electricity and the magnetic field are directly related. So when one goes up, the other one goes up. The direction of the magnetic field, like I said before, the direction all depends on the flow of electrons. If the electrons are flowing to the left, then it's going to move to the left. If the electrons are moving to the right, it's going to move to the right. Right means counterclockwise. I mean, where I'm reversed from you. So if the electron flows to the right, it's going to move to the right. If the electron flows to the left, it's going to move to the left. And that just means reverses polarity. The polarity is the poles, north to south. So if you reverse the polarity, if you go from north to south, okay, it's going to flow, to the left. If you change the polarity and go from south to north, then it's going to flow the other way. It's just the way it is. Now, we use electromagnets in our lives all the time, all day, and we don't even realize it. So if you use a debit card, or if your parents have a credit card, debit card, that has a small electromagnet in it. Because if you notice, they walk up to a pin pad at the Walmart or any kind of store, and they touch it, they can just touch it, and it reads the information. The most common one we probably remember is this large machine at a junkyard that moves the scrap metal from one part to another. The operator will move this big hand claw over to a pile of metal, and it will turn on the electricity. And when it turns electricity, the electromagnet will pick up the metal, and it will move it over to another place, and then it will turn off the electricity, and it will drop everything because it's not magnetized anymore. Speakers. The speakers in your car, in your earbuds, in your everything has a magnet, because it has to pull the coil back to be able to make sound, to vibrate the air. So we use magnets there. Another common place is the doors at school. The outside doors that the teachers have the key card, those little cards have electromagnets in it. And actually the door is being held closed by an electromagnet. So when a teacher comes to the door and they scan their card, the door, the lock recognizes that it's a good card, and so it turns the electricity off to that magnet, and we're able to open the door. If you've ever tried to open one of those doors without scanning your card, you'll notice that it's almost next to impossible. The magnetism is so strong in those doors. MRIs, the MRI machine at a hospital, it has the word magnetic in the very, very beginning of it. Magnetic resonant imaging. So it uses big magnets that go around and around, and it shoots a signal into your body. Sorry, the lights went off. And that is how we that's how the image is seen for your soft tissue inside of your body. So these are just a few ways that we use electromagnets in our everyday life. This bullet train is pretty cool. You should look that up. That's how it moves really, really fast from one part of the city to another. Now, solenoid. A solenoid is just a fancy word for a single wire wrapped into a cylindrical wire coil. This could be a solenoid here, but the most one that we're going to look at is if you take a nail, such as this, and a wire, and you take the wire and you wrap it around in a coil-like fashion. So I'll wrap it a few times and let you see it. You see that? See, when you wrap it around in a coil-like fashion, okay, you are essentially making that wire really close together. And like I said before, if you have the wire stretched out and the magnetic fields that are running across the wire are very weak, but when we wrap it around this, like this, we're making those coils really, really tight. And so when we wrap it around an iron core, okay, and then we put electricity through it, then we create an electromagnet. So something like this nail could be an electromagnet as long as it has an iron core. Okay, it can make an electromagnet. So to summarize what we talked about in this video, electromagnetism is the interaction between electricity and magnetism. It was first discovered by Hans Christian Ørsted whenever he was experimenting with electricity, and he set a compass near a wire, and he saw that compass move. So when that compass diverted its path, he noticed that there was a relationship between electricity and magnetism. Moving charges, electrons in a current wire, electric current, the moving electrons in a wire produce a magnetic field around that wire. If it's stretched out, it's a very weak magnetic field. But whenever we put those coils together in a cylindrical form, we actually create a coil called a solenoid. And that solenoid produces a magnetic field that is stronger when they're bunched together. All right, so that is the basics of electromagnets. Again, if you have any questions, please go back and rewatch the video, or if you missed any notes, and have a good one.